Welcome to E-Padasala lecture series in computer science. Today we are going to discuss about dynamic programming strategy. You can recollect for the past few modules we were talking about dynamic programming strategy. Today we are going to discuss about some interesting problems in dynamic programming strategy to illustrate those concepts. The learning objectives of this particular module are to explain dynamic programming. Already we had discussed that dynamic programming is one of the most popular design strategy in algorithm design. We had discussed lots of problems as part of that. This module we are going to concentrate on binary search tree. We are going to discuss about the fundamentals of binary search tree. Then the focus of today module is going to apply dynamic programming strategy for finding the optimal binary search tree, which is one of the most important problem in algorithm design. What is dynamic programming? Probably you can recollect for the few modules we were talking about this. So, like divide and conquer, in dynamic programming we are going to take a problem and we are going to divide that problem into number of sub problems. The nature of dynamic programming is that these problems have to be overlapping sub problems, and once we have this criteria we can establish the recursive property that give solution to the instance of the problem. So, recursive property is going to establish the relationship between the problem and its sub problems, and we had seen as part of the strategy we are going to develop a table and we are going to enter the solutions of the smaller problems into the table. So, the larger problems solutions are obtained by combining the solutions of the sub problems in the bottom up fashion. So, the key of this strategy is to reuse rather than to recompute. That is the reason why dynamic programming are faster. Probably you can recollect we had discussed the advantage of dynamic programming over divide and conquer strategy. In divide and conquer strategy always the problems are independent of each other, but whereas in dynamic programming the problems are overlapping problems. Second thing is dynamic programming establish the property of global optimality. Therefore, we can get better solutions as part of the dynamic programming approach. Today, we are going to discuss about one important problem called binary search tree. So, what is a binary search tree? A binary search tree is a special kind of binary tree. Probably in one of the earlier modules you would have seen we defined what is a binary tree, a tree where the node can have 0 or 2 children. So, in the binary tree we have various types. The binary search tree is one of the most important special kind of binary tree. So, the unique feature of the binary search tree is that the elements on the left subtree will have keys that are smaller than the key of the root, and all the keys on the right side of the tree are going to be greater than the element of the root node. So, this is a unique property that establishes the characteristics of a binary search tree. More often when we try to develop a binary tree, we may end up a binary tree something like this. For example, what I am trying to do as part of this is that I have taken 4 keys 10, 9, 8 and 7, and I am trying to develop or construct a binary tree. So, nothing wrong with this particular tree, but this is a skewed one towards the left directions. In other words, this tree is not a balanced one. Therefore, to avoid this, there is a necessity to balance the tree. So, in binary search tree, what we are trying to do is we are trying to construct the BST in a balanced manner. Once we have a balanced binary search tree, then we can retrieve the key using this particular algorithm. So, if I want to retrieve the node x, then I am going to compare x with the root element of the binary tree. If the binary tree is going to be a non-empty. If the binary tree is empty, then we are going to return a null value. That means, there are no nodes that are present in that particular tree. Otherwise, we have some elements, and x, if it happens to be in the root, then we are going to return the address of the root node as the value of x. Otherwise, as we discussed earlier, we are going to go and traverse the left tree if x is less than what is present in the root node. Similarly, we are going to traverse on the right side if the node is greater than the element in the root. So, in this process, the traversal is carried out till we get the information that whether the item x is present in BST or not. These sort of BSTs have got immense applications in computer science domain. One of the major usage of BST is in dictionary construction as a part of compilers, where we are going to develop some sort of a symbol table, where we are going to store all the identifiers, variables and operands, so that the retrieval time is going to be faster. This is one of the primary motivation behind the concept of the binary search tree. Fine. Let us take one simple example. Let us try to construct a BST. So, let us take 3 keys and let us assume that these are the various probabilities. Probability comes suddenly here because every word, every key occurs with a frequency. So, let us assume that there are 3 keys with the probabilities of 0.4, 0.3 and 0.3. So, recollect the rules of the BST tree. So, as I said earlier, all the nodes on the left hand side should be lesser than the value of the root node, and all the elements on the right hand side is going to be greater than what is present in the root node. So, for our key set, that is A1, A2, A3, this is one such possibility. Suppose if I construct like this, can I associate a metric for this particular construction? Means I can do that, and let us assume that a cost metric is assigned for this particular tree construction. The cost of the BST is computed by multiplying the level and the probability of occurrence. So, you recollect the concept of level in the earlier module. So, the root is always in level 1 and all the nodes are away from the root. So, the path length indicates the level of that particular node. So, in this particular case A3 occurs in level 1. So, it is 1 into 0.3, A2 occurs at level 2, therefore, it is 2 into 0.3 and A1 occurs in what is say level 1. So, that means it is going to be 1 into 0.3. A2 occurs in level 2. So, it is 2 into 0.3 and A1 occurs in level 3, therefore, it is 3 into 0.4. So, put together the cost of this particular tree is going to be 2.1. There are other possibilities of constructing the BST without violating the norms as we defined earlier. So, the same nodes, 3 nodes can have different possibilities. These are some of the different possibility where the conditions are not violated. So, if we assign the same metric cost for every tree and by multiplying the level and the probability of occurrence, we can see that the cost of the tree is going to be different. So, that means you can see that every tree is now associated with a particular cost. So, you can see that this is going to be an efficient strategy, because this is a tree that is associated with the least cost. So, the concept of optimal binary search tree comes into picture whenever we are seeking a minimum cost for the constructed BST tree. So, the problem of BST can be defined like this. We have a set of keys and every key is associated with a probability, and the aim is to construct a BST with the minimum cost. The key of this particular problem is the minimum cost. So, the question is given a set of keys, any arbitrary keys A1 to AN or K1 to Kn. The question is how you will construct the tree such that the cost is going to be minimum. Fine, why can't we try out using the brute force approach? Means it is possible. So, what we can do is we can take the set of nodes and we can construct all possible combinations by assigning keys, and we can compute the expected search cost. This is going to be the brute force strategy for finding that particular cost, but unfortunately this brute force technique will not be put into practice, because as n increases, the number of possibilities also increases. In other words, if we take nodes 1, 2, 3, 4, 5 etc., you can see that it follows a sequence called the Catalan sequence. So, the Catalan sequence is shown in this particular slide. So, it is C of n is 2n C n multiplied by 1 plus n for n is greater than 0, and C of 0 is going to be 1. For example, if I want to compute the third Catalan number, it is going to be 1 by, so 3 plus 1, then 6 C 3. So, you can see that it is going to be 5. In other words, this Catalan sequence tells us how the possibilities increases with the value of n. So, it is going to be what you say omega of 4 power n divided by n power 3 by 2. In other words, this is going to be an exponential problem, and as n increases, the number of possibilities becomes more and more, and it is practically difficult to implement these sort of problems. So, that is the reason why we are going for some sophisticated methodology, and this sophisticated methodology happens to be what you say dynamic programming. So, in dynamic programming, so we can apply the concepts to this particular problem. So, what we can do is we can take the set of keys a1 to a n. So, we can take an arbitrary element called a k, and we can construct the left subtree. So, that the left subtree a k consists of elements a 1, a 2 up to a k minus 1. Similarly, the right subtree of a k is going to contain the keys a k plus 1, a k plus 2, so on up to a n. So, in other words, what we can do is we can construct the tree using the arbitrary a of k, and we can find the cost. Can we apply the dynamic programming strategy for this? Means yes, we can do that. What is the reason? The reason is like this. I was telling you that dynamic programming can be applied for two cases. Number one is the optimal substructure, and second is you have overlapping subproblems. What is the optimal substructure? Probably you can recollect we were talking about this as part of principle of optimality, which tells us that the optimal solution for a problem contains the optimal solutions for all the subproblems that are contained within this particular optimal problem. In other words, if T is going to be an optimal BST, and if we are going to construct a subtree T prime with keys k 1 to k n, then T prime is also an optimal BST for keys k 1 to k n. So, the optimal principle holds good for this particular thing. So, in other words, if the principle of optimality holds for the tree, then the principle of optimality holds good for both left subtree as well as the right subtree. Therefore, the dynamic programming is more apt for this particular problem. Fine. What is the idea? The idea is very simple. The idea is to construct the optimal BST. So, what we are going to do is we are going to examine all candidates for the root element a k, where k ranges from 1 to n, because the given elements are a 1, a 2, a 3 up to a of n. Therefore, the k ranges from 1 to n. Now, we are going to determine all optimal BSTs for a 1 to a k minus 1 and all elements from a k plus 1 to a n. You can see exactly what is happening here. As I said earlier, the problem is divided into two subproblems. So, what we are going to do is we are going to examine a candidate for a of k, and accordingly we are going to divide the problem into problem of constructing BST for keys from 1 to k minus 1 and k plus 1 to a of n. So, now we have two subproblems which can further be divided into further two subproblems. In that particular manner, we have the number of subproblems from the original problem. And incidentally, all these subproblems happens to be what you say overlapping in nature. Therefore, we can come to a conclusion that dynamic programming is apt for this. So, this is the informal algorithm. So, informal algorithm is step 1, we are going to read n symbols and all symbols are associated with a probability p of I. So, as I said earlier, as dynamic programming we are going to construct a table. So, C of I comma j, where every entry is going to illustrate how or the minimum number of cost that is required to compute that particular BST. So, we are going to initialize a table C of I minus I to P of I and C of j minus 1 comma j to 0 for all elements I belongs to n. Now, comes the crucial part, that is establishing the recursive definition of this particular problem. The recursive definition is very simple. As I said earlier, we are going to consider a k. So, using that we are going to divide the problem into two subproblems. So, the cost of computing that is going to be the cost of 1 to k plus 1, then C of k plus 1 to j and P of m, where m ranges from n is going to what you say find the number of computations. Finally, what happens is we will be reusing the concept and the final C of 1 comma n is going to be sent as the cost of establishing this. Fine. Now, we will take one simple example of how to construct the cost of C of 2 comma 3, where keys 2 as well as key 3 is given. So, probably now you can recollect that there are only two keys, key 2 and key 3. So, what are the possibilities? Two possibilities are there. So, that means on left hand side you have one possibility and on the right hand side you have another possibility by sticking to the norms of the binary search tree. So, now what we have to do is we have to establish the cost and we have to take the minimum cost and we have to enter that as the value for C of 2 comma 3. In other words, C of 2 comma 3 is going to contain the value of the minimum of all the possibilities of construction involving keys 2 as well as 3. Probably now you would have got the gist of what this algorithm says. The algorithm says we have to establish the recursive function. So, by changing the value of I and j, so we are going to think about the various possibilities and then we are going to enter the minimum of the cost into the particular table and as we progress, finally, we will get the value for C of I comma j and that is going to be the minimum cost for constructing the optimal binary search tree for that particular key set. Difficult? No, it is not, because we are not going to recompute everything, but instead we are going to what you say apply the recursive definition and then we are going to find the value. In other words, we are going to use the concept of reuse rather than what you say recomputing of everything. So, finally, when you develop a table like this, you will get a table. So, you can see that on this side you have I. So, on this side you have j. So, you can see that P 1, P 2, P n are the various probabilities that are associated with the given elements, and we are going to compute C of I comma j, and finally, C of 1 comma n is going to contain the minimum cost that is required for establishing this. This is the idea behind the whole thing. Fine, we will take one simple example. We will take 4 keys. As I said earlier, it is useful for containing symbol table. It is useful for having various symbols. Let us have 4 symbols: Danny, Ian, Radha and Z. Let us assume that these are the various keys 1, 2, 3, 4, that is A, B, C, D, and let us assume that these are the various probabilities that are associated with all these key. So, the question is very simple. Given these 4 keys, the question is how to construct the optimal BST for this particular problem. Fine. As I said earlier, brute force method is not possible, because brute force method requires finding out all possible combinations, which is going to be very tougher. So, let us try to apply the dynamic concept, dynamic programming concept. This is how the table looks like. So, you can see that there are 4 keys. So, it starts from 1 to n plus 1. So, that means it is going to be 5, and on this side we have 4 keys. So, it ranges from 0 to 4. So, now this is the initial structure of the table. Initially C of 1 comma 1, that is you can see that it is going to be 2 by 7, that is given as part of the problem. 2 by 2 is going to be 1 by 7, and 3 comma 3 is going to be 3 by 7, and 4 comma 4 it is going to be 1 by 7. So, this is how the initialization looks like, and you can see that 1 comma 0, then 2 comma 1, 3 comma 2, then 4 comma 3 and 5 comma 4 are all going to be 0. So, now this is how the initial table is going to look like. So, now our next target is we want to find out 1 comma 2. So, that means we have 2 keys, that is A 1 and A 2. So, recollect the instance that I gave earlier. So, 2 keys means there are 2 possibilities. So, that means you can have A 1, then A 2 as a subtree of that, and another way is you can have A 2 as a root node and you can have A 1 as a subtree adhering to the rules of the binary search tree. There are 2 possibilities. So, using that we are going to find out this particular entry. So, you can see exactly how it is happening. It is going to be application of the recursive function. So, recursive function we have seen already. So, it is going to be C of 1 comma 0 plus C of 2 comma 2, then we have summation of P m, where m ranges from 1 to n. So, that means we have 2 elements, therefore, it is going to be P 1 and P 2. So, this is when k is equal to 1, and when k is equal to 2. So, it is going to be C of 1 comma 1 plus C of 2 comma 2. So, this is when k is equal to 2, and this is when k is equal to 2. you have this. So, similarly, we are going to find out C of 2 comma 3 and we are going to find C of 3 comma 4. So, what we are going to do is we are going to take the minimum of all the things which happens to be what you say 4 divided by 7 and here you have 6 divided by 7 and here you have what you say 5 divided by 7. So, using this particular we can find out this particular diagonal. Next we have to find out this. So, that means it is 1 comma 3. So, 1 comma 3 means you have 3 keys. So, you have different possibilities. So, again you try to compute that by means of your recursive definition. So, it is going to be C of 1 comma 0 plus C of 2 comma 3 which already we have computed. So, 3 elements. So, it is P 1 plus P 2 plus P 3. Similarly, you can say it is going to be C of 1 comma 1 plus C of 3 comma 3. So, similarly, you can see that another possibility is C of 1 comma 2 plus C of 4 comma 3 plus P 1 P 2 P 3. So, you can see that the minimum of that is going to be what you say 10 by 7. So, similarly, we can find C of 2 comma 4. So, that means the problem of finding BST with elements 2, 3 as well as 4. These are the various possibilities and you can see that it is coming as 7 by 7. So, this is what it is. So, now we can enter that into this particular table. So, you can see that it is going to be 10 by 7 for between 1, 2, 3 and similarly you can see that it is going to be 7 by 7. So, now we have to find out only one thing, that is 1 comma 4, that is what our goal is. So, again by applying the recursive definition we can see that it is going to be what is a minimum of all these factors which turns out to be what you say 12 by 7. So, now we can put everything into this particular table. So, now you can see that 12 by 7 is going to be what is a 1 comma n, that is going to be 1 comma 4. Therefore, we can say that this is going to be the optimal cost for constructing the tree structure. Fine. So, now we have seen what is the optimal cost, but what is a tree? So, using the same logic as we discussed earlier problems, what we have to do is we have to establish another table where we have to enter the value of k which gave the minimum. So, in other words, whenever we are trying out all these possibilities, we have to find out the minimum k that we have to enter into the particular table. So, that is what you can see is entered into this particular table. So, now you can see that this is a table where all these minimum k are recorded. So, now using this we can easily find out how the tree is going to look like. So, now you can see that it is 1 comma 4. So, that means 1 comma 4 is going to be 3. So, that means A 3 is going to be your root node. So, now you can see that using this you can see it is going to be a root key A 3, that is going to be your Radha, which happens to be the root node. So, now you can see it is it is going to be 1 comma 2 is going to be 2. So, that means A 2 is going to be the root node and you can see that from this particular table we can find the corresponding entries, and using which we can find what you say the right child for these things. In other words, this is what the generated BST is going to look like. So, in other words, this is what going to see. So, in other words, from the minimum k we can easily construct how the binary tree has to be constructed. So, this is a formal algorithm. Formal algorithm, you can see exactly what is happening. N keys are given. So, we are starting a loop. So, we are having this particular algorithm where we are initializing the table, then we are initializing the table for R. So, this is what going to contain the minimum value of k, and you can see that this is the loop where we are going to construct the entries for the upper triangle. This is a recursive relation. So, finally, we are going to return 1 comma n as the results. This is the complete algorithm for this, and what is the time complexity? Time complexity is going to be theta of n cube, but taking the advantage of the monotonicity where R of phi comma j is always going to be in the range, we can say that this can be reduced to what is a theta of n square, and what is the space efficiency? It is going to be theta of n square. In summary, we can come to a conclusion that dynamic programming is a very effective technique. Dynamic programming can solve the optimal binary search problem effectively. Thank you very much. Next module we will come up with fresh set of problems for dynamic programming approach. Thank you.